Right, let's have a quick look at the Texas Instrument calculator. This is part 2 of using the calculator. In part 1 we looked at some of the keys, or most of the keys on the calculator, not quite all of them, but you should have a fairly good idea now about the basic functioning of the calculator. And now we're going to apply what we know in conjunction with the formula sheet that you're going to be given in the examination. Now, we're not going to necessarily do all of the formulae, and in fact this will probably have to be split up into various parts. Also, don't be intimidated by the fact that you may not understand the basis for the formula at this point, because that will be covered in videos and in the course anyway. Some of it you will already know from the foundation course. So let's have a look at the top left of the formula sheet. On the first row we've got RT equals R1 plus R2 plus R3. Now the formula sheet doesn't say what things relate to, it's just, if you like, a memory jogger, an aide-memoire, and it's up to you to be able to think and apply this to the various situations that you encounter. So this one, I think you'll probably realise from the intermediate course, relates to resistors in series. So what we've got here is 3 resistors in series, but of course it could be 2 resistors, 3 resistors, 4 resistors, or whatever. The same principle applies, that when you've got resistors in series, you simply add them up. So this is the circuit that it's relating to. And you've got R1, R2, and R3. And if you looked in the terminals there with your eye, you would see, looking in there, an equivalent resistance, or the total resistance RT. And that's what the formula there relates to. So if we put some values on that, let's say 5 ohms, 10 ohms, and 15 ohms. We switch on our calculator. It's simply a matter of saying 5 plus 10 plus 15 equals. And the equivalent circuit then would look like this. A single resistor of value RT is equal to 30 ohms. So that's simply adding resistors in series. If we had something slightly more complicated, if we replaced one of the values there with, let's say, take this value here, the 15 ohms, and we'll rub that out. And if we said there it was 0.05 kilo ohms, how would we simply enter that into the calculator? Well, we could press all clear, and we're going to be using here engineering notation. So we would switch the calculator into engineering notation. That's second function eng, which is the 6th key, and we can see then that the calculator is in eng mode because the enunciator is up there, and we'd also see that we've got the 2 little zeros there indicating that it's in engineering mode. Okay, so at that point then if we put onto it then 5 ohms, 5, okay, plus, oops, sorry, I don't seem to be in engineering mode. Yes, I am, yes, plus 10, and we can put plus 0.05 EE, and we're in kilo ohms, 3, equals, and that will give us 65 ohms. So let's look at the keystrokes for adding that then. We put in, first of all, we put the on clear, and then we use second function EE, and at that point we can see the enunciator on the screen. We then put in 5, and that's 5 times 10 to the 0, so we don't have to put in anything else, plus 10 plus 0.05, and then we press EE 3 because it's kilo ohms, in other words 0.05 times 10 to the 3, and then the equals key, and then we have 65, and the units are ohms. So you can see then that the EE key, and using engineering notation, makes it fairly easy to enter the values that we need. So that's resistors in series. If we scroll to the right, on the top row, we see a formula here for resistors in parallel. And it's 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc. And there is a video on resistors in series and parallel, which I urge you to look at. In the intermediate course, we only had to work out the equivalent resistance, or the total resistance, where we had 2 resistors or 3 resistors of equal value. And we simply took one value and then divided by the number of resistors. But when the resistors are not of equal value, we have to use this formula. So let's have a quick look and see how that looks. So the circuit looks like this. Here's the first resistor. Here's the second resistor. And here's the third resistor. And the principle can be extended to any number of resistors. In fact, it works, as the video says, between one resistor and an infinite number of resistors. So here we have R1, R2, and R3. And we're asked to find out what RT is. The total resistance, if we're looking in there. In other words, what single value would be equivalent to those 3 resistors in parallel. So let's put some values on them again. Let's say that this one would be 10 ohms, 15 ohms, and 20 ohms. So let's put the 10, the 15 and the 20 in the calculator. So first of all, we can clear. We can go second function float, because we don't need to use anything else at the moment. to enter it. We've got no kilo ohms or milliohms to enter, so we can leave it in float, or we could leave it in engineering. It doesn't really matter. So let's put in R1. That's 10 ohms. And we need to find out 1 over R1. If you look at the formula there, we need to find 1 over R1. Now we could have put in 1 divided by R1, but we've got the reciprocal key, and that's the key here. So it's a simple matter of just pressing the reciprocal key. So that gives us 1 over R1. Now we can say plus R2, which is 15. Take the reciprocal of it. And then plus R3, 20, and take the reciprocal of it. And on the screen we've got 0.21. So what we're saying is 1 over RT is equal to 0.216, etc. So now we need to find RT. So it means taking the reciprocal of both sides. So RT over 1 will equal 1 over 0.216. So this is an equation, and what we do to one side with a single term, we can do to the other side, provided there are single terms on either side. So we've taken the reciprocal of that, RT over 1 gives us RT, that's what we're looking for. So we have to take the reciprocal of 0.216, and that's there. Well, the 0.216 is already on the screen in the X register. So we simply press 1 over X, and there is our answer. Our answer, RT, is equal to 4.615, although we won't need this sort of accuracy, ohms. And you can see the result there on the screen. So to recap on that, where we have resistors in parallel, and we need to find out the total resistance of the resistors in parallel, or the equivalent resistance, we need to use the formula 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. We put in the values of R1, R2 and R3, and we use the reciprocal key, 1 over X key, to give us 1 over R1. So once we've added up those reciprocals, we have 1 over RT equals a certain value. And we have to take the reciprocal of the answer of the answer of 1 over R1 plus 1 over R2 to give us RT. And I've shown that here on the screen here. So you should practice these, because if you look at capacitors in parallel, or I beg your pardon, capacitors in series or inductors in parallel, you'll find the same form of formula, where you need to add up the reciprocals of the values and then take the reciprocal of the answer. So that's a good one to practice. Let's have a look at the next one. There are 3 columns there. The next one is simply V equals IR. We know that one from the intermediate course. Remember, we had the triangle V, I, and R. But now we can get to the forms of the equation another way. we can use algebra. There's nothing wrong with using the triangle, but if you want to get to the three forms of the equation, you can use some algebra to derive from that one the other two forms. And you do this by recognizing it's an equation, it has to balance. So if we divide both sides of this one by I, first of all, we get V over I equals R. I divided the V by I and the IR by I, so the I would be on the top and bottom, and therefore cancels, so that's the second one. And I can also divide, I can take this first equation, okay, and I can say I'll divide both sides by R. So I can say V over R equals I. So therefore, I've got the three forms of Ohm's law, the VIR equation. Let's look at an example then. If there was a simple circuit with let's say 6 millivolts voltage source and a 5 kilo ohm resistor, what would be the current? Well, the current would be I equals V over R. But here we're using some multiples and submultiples, and the easy way is to get the calculator to do the work for you. So press clear, go to second function engineering, and confirm that you're in engineering. You've got eng at the top and the 0 there. It doesn't matter, you can always go back later on and enter in the put it into engineering mode. It's not critical that it starts off in engineering mode, but it's convenient. So we're looking for V over R. We're looking for what we want to solve is 6 millivolts, which is V over 5 kilo ohms, and that's the I equals. So we enter 6 EE 3, and that's 6 kilovolts, but we want millivolts, so we press the change sign button. And now we've got 6 times 10 to the minus 3 on the top line. You can see the 6 and then the minus 0.3 shown there. Now we divide that by, so press the divide button, 5 EE 3 equals, that's 5, that's minus 3, and the answer comes in as 12 times 10 to the minus 6. You can see 12 and minus 6 there. That's I. And because we entered the values here in volts and amps, volts and ohms, then our answer will of course be in amps. So that's 12 times 10 to the minus 6 amps. And you should be remembering by now, minus 6 is micro. So we're looking at 12 micro amps. Now that's a very small current. Let's just do a sense check on that, a sanity check. Well, we've got a very small voltage, only 0.006 of a volt, and we've got a very high resistance, 5,000 ohms. So we'd expect with a very low voltage and a very high resistance that a small current would flow. So on the surface that seems quite reasonable. So I'm happy with that. So that's V equals IR. Let's go down and look at the second row then. I'm going through this row by row because it's probably the easiest way. It may not be the easiest way to learn, but it's certainly the easiest way to find your way around the formula sheet. And there are a lot of formulae on the formula sheet. So let's have a look at the next one. The next one says V out equals V in R2 over R1 plus R2. Well, you might say, and quite reasonably, well, what is R2 and what is R1 and what does this relate to? Well, it's only by working through the course that you could possibly know. If anybody were given this, they could quite justifiably say, well, what does this refer to? Well, I guess the answer is it just refers to what's in the syllabus of the radio amateur exam and the advanced course, and in this case it refers to a potential divider. So we haven't covered potential dividers necessarily at this point, but if we had, for example, two resistors in series across the source of EMF, and we call the source of EMF V in, then halfway down the two resistors we'd have a different voltage V out. And this equation, the one on your screen there, allows you to calculate what V out is. So we have to be able to label these. This one is R1 and R2. If they were the other way around, the formula would be incorrect. So we have to have knowledge of what they're getting at, what they're talking about. But given that we do know what they're talking about because we will have done the course, then here's a potential divider. And for example, if there were 6 volts at the top of the resistor R1, then as you go down through these resistors, you eventually get to the bottom of R2 where there is 0 volts, because if you like, that could be plus and that could be 0. So what you're seeing here then is a potential gradient from the plus at the top to 0 volts at the bottom. And all voltages between whatever V in is and 0 will exist on this potential gradient. So the question is, what exists at this point? Well, there's the formula then. V out equals V in R2 over R1 plus R2. So let's put some values on this. Let's say this one is 10 ohms and this one is 20 ohms, and V in is, let's say, 6 volts. So we're saying V out equals R2 divided by R1 plus R2 times V in. So let's go ahead and do that now. Turn the calculator on. We might as well go into float. That's clear. And we have a 0 on the screen. So we can use brackets here to make this an easy calculation. So we can enter it pretty much as we see it. We can say, first of all, R2 divided by R1 plus R2. Let's do that fraction first. Let's look at R2, which we said is 20. And then we can divide that by, now we want to divide it by a result of R1 plus R2, so it's safe to put brackets around it. We put a bracket, it doesn't show on the screen, but it's implied. R1 plus R2 is 10 plus 20, and then we close the bracket. And then we can say equals. And that has given us the term R2 over R1 plus R2. Now we can multiply that by V in. So we say times 6, and then press equals, and that will give us 4 volts. And we'll do a quick sanity check on that. We've got a potential divider there of 10 plus 20, so that's 30. And we're saying that 2/3 up the potential divider, 20 out of the 30, going up from the bottom, the voltage is 2/3 of the voltage in. 2/3 of 6 is 4. So that makes sense, and the sanity check works. Let's go through the keystrokes of that again. So here we need to know a little bit about it's kind of practice of the best way to do it. The best thing to do is to get rid of the fraction term first. So let's have a look at that. Let's do that again. So what we did is we said R2, which was 20, divided by, and then we need to clump the R1 plus R2 because it's 20 divided by the sum of R1 plus R2. So we've pressed the bracket. I'll start again. 20 divided by, open bracket, 10 plus 20, close bracket. And you can see that's given us 30. Now we press equals, which will give us the evaluation of this term here. That's now 30. Is now 0.6, which you can see, 666, which you can see on your screen here. And now we need to multiply that by V in. So times 6 equals 4. So that's the potential divider. Don't worry if you haven't come across it, but try and understand the keystrokes for using the calculator to evaluate that equation with those values. Okay, let's have a look along on the second row. And here we've got 3 equations in one, if you like. And let's spend a bit of time to go through this one. I think there's a video then looking at how these are derived. Remember that you know that V equals IR, R equals V over I. These should be very familiar to you by now. And I equals V over R. And you know these from the intermediate course. Also remember that you know that P equals VI. And you know that from the intermediate course. The power dissipated in a resistor is equal to the voltage across the resistor times the current through the resistor. P equals VI. P is in watts. So, looking at the equation there that you see on your screen, that is the first representation of power. The second one is obtained by substituting for I, V over R. If I equals V over R, then you can write V over R instead of I. So that's V times V over R, which is V times V, anything times itself is squared, is V squared over R. So that's the second representation of power, which you see from the formula sheet. Then I'll write P equals VI again. This time I'm going to substitute for V. I look up here, I know V is IR. So instead of writing V here, I'm going to write IR. So it's equal to IR times that I. So I times I is equal to I squared, and there's the R. So that's the derivation of the three forms of the power equation. You don't need to be able to look at the sheet to do this if you're able to derive it from first principles, which we've just done. If you can't, at least you know that it can be derived from first principles, and you can simply look at the formula sheet that you're going to be given in the exam. So let's do a calculation then of V squared over R. We won't do VI because we should by now be able to multiply two numbers together. But if we say that P equals V squared over R. So let's have a look at a simple circuit. Here is R. And let's say there's 6 volts and there's 10 ohms. Now with your knowledge from the intermediate course, you could work out the current flowing around that and then do P equals IV, and that would be fine. So the current would be 6 over 10, which would be 6/10 of an amp, and you multiply that by 6 volts, you would get to 3.6 watts. So you could do it in 2 stages, or you could go straight to the answer by using this formula here. You've got V and you've got R, so you can go straight to the formula. Let's go to the calculator. We press clear, and we've got 0. We press 6. Now, we've got an x squared button here, so we can just press x squared, and that gives us V squared, which is, so let me write it, 6 squared over 10. So we've done the 6 squared, which is 36, which is on the calculator. Now we need to divide it by 10, equals 3.6 watts. So that's used the formula V squared over R, V squared over R, to give us our power. Let's do another one, but using I squared R. P is equal to I squared R. And we would use this where we know the current and the resistance, but we don't know the voltage. Here we have the resistance. We've got a voltage which we don't know, but let's say we do know what the current is. Let's say the current I equals 20 amps. And let's say the resistance R equals 10 kilo ohms. That's a high current, and a high resistance, so I'm expecting a high voltage, because the voltage is what pushes the current around the circuit. Let's work it out. So first of all, let's work out I squared. Put in 20, and then press the X squared button. And we get 400. So we can write that down. Don't have to write it down, but for illustrative purposes we would do. Now, times R, which is 10 kiloohms. So I'm going to write in 10 EE 3. Now I'm going to press equal sign, and I've got 4 million. 4 million. So times 10 to the 3, and it's come up on the screen as 4 with 6 noughts. Notice I didn't have to be in engineering mode to use EE to enter it, but unless I'm in engineering mode, the answer will come out, if it can, as a float. So now I'm going to put it into engineering mode, second function engineering, and I get 4 times 10 to the 6 watts. The power is in watts, so 4 times 10 to the 6 watts. In other words, I would have 4 megawatts. A lot of current through a very high resistance is going to give me a lot of power. So those are 3 forms of the power equation, which we'll be going through and practicing as we go through the advanced course. So remember then that you can use the EE key at any time to enter a value, mega, kilo, micro, but it's important that one of the early things you do with the advanced course is learn the correspondence between, for example, times 10 to the minus 3 being milli, 10 to the 9 being giga, etc., etc. So you need to know all of those multiples and submultiples to the extent that they become second nature, so that when you want to enter in 5 milliamps, you just put in 5 times 10 to the minus 3 amps, and you put it straight into the calculator, and you can then toggle between seeing the result either in engineering notation or float, or if you're so minded, even in scientific notation. So let's move on then to the next formula. This one will be familiar to you. V RMS equals V peak over root 2. In the intermediate course, we learnt that if you have a waveform that is an AC waveform, whether it's current or voltage, then that is the peak value. That is the peak to peak. And RMS, okay, is 0.7071 times the peak. Now the RMS value, if you recall, provides the same heating effect in a simple circuit in a resistor, for example, as if it was a DC value of the same value. So for example, if we had 10 volt peak and we had 7 volt RMS, the resistor would get equally as hot. Let's have a look at that. So if you had a simple circuit with a battery and a resistor, and the battery was 7 volts, that would be the same as having an AC source. The temperature of the resistor would be the same as having an AC source of 10 volts peak, and that's 7 volts DC. So that would give you the same amount of heat coming off as if it was a battery with 7 volts. Now, how is that actually derived? Well, 1 over root 2 is 0.7071. I think in the intermediate course you had a choice of using 0.7071 or 1 over root 2. It's the same thing. Let's demonstrate that. If we press clear on our calculator and we press 2 and take the root of it, it says 1.4142. And then we take the reciprocal of it, it's 0.7071. Let's look at the keystrokes there to work out what 1 over root 2 equals. So the keystrokes are, let's evaluate the root 2 first. 2 root, so 2, and then root x key, and at this point you have evaluated this term here. And in your screen you will have 1.4142. But you want 1 over root 2, so now you need to press the 1 over x button, the reciprocal button here, which is above the EE button, and it gives you 0.7071, etc. Let's do an example then. Let's say we had a circuit with 55 volts peak. What are we saying there? We're saying there's an AC waveform and it goes plus 55 and minus 55. And that's the peak voltage. What would the RMS voltage be? So RMS, okay, VRMS, and the formula there is equal to V peak, 55, divided by root 2. And where you've got terms that need sorting out with the function keys, it's sometimes easier to address those first. So we can work out, and press the clear key, we can do 2 square root, that's the way I would do it, okay, divided by 55. Now I've got it upside down. I've done here, not equal to, but I've done root 2 over 55. And I have an answer which is 0.025 on the screen. I now can flip that the other way up to get 55 over root 2 by pressing the reciprocal button. And I get the answer, 38. And that seems to make sense. That's about 0.7 0.071 of the way up towards the 55, if you like. I could do another sense check. I could go 55 times 0.7071 equals, and again, I have 38. So that's the formula and the use of the calculator for working out the RMS value if you're given the peak value. Now, by now you might be getting a little bit good at algebra, if you're not already good at algebra. So here we have the formula V RMS is equal to V peak divided by root 2. So what happens if you're given VRMS? You're given essentially this. You're told that you're given VRMS and asked, what is the peak value? Well, you can go to this formula here and you can rearrange it. Remember that this is an equation. What you do to one side, you do to the other. So I want to get V peak on its own, but it's V peak over root 2, which is awkward. So if I multiply both sides of the equation by root 2, I will leave V peak on its own. Let's try that. V RMS times root 2 is equal to V peak times root 2 over root 2. So I've multiplied both sides by root 2. And I've got root 2 on the top of the fraction and root 2 on the bottom of the fraction, so I can strike those out. And now I've left V peak by itself. So I can restate that formula as V peak is equal to VRMS times root 2. Let's say I was given a VRMS of 38 volts. Let's try it. I've probably got some rounding errors here, but I'm expecting to get a V peak of about 55. So let's have a look. I can put in 38 times root 2. Well, I'll do the root 2 first. So I press 2 and square root. That gives me 1.4. And I can multiply that times 38. And I get 53, nearly 54 volts. Now it isn't exactly the same as before because I ignored the decimal places, but basically if we put in 38 here as VRMS, we'll get a V peak of about 54 volts. So that's how you can manipulate a formula. Remember, if it's an equation, and it's always an equation, it has an equal sign. As long as you do to the left, entirely to the left, what you do to the right-hand side, then you can manipulate the formula. Right, let's have a look at the next one. Third row. So this formula relates to capacitors in series. Now, when you're looking at the stuff you get presented with in the advanced examination, basically we're dealing with capacitors, inductors, and resistors. So when you've got resistors in series, you add them up. Let me just do two columns here. So you have resistors then would be RT is equal to R1 plus R2 plus R3, etc. Inductors, remember inductor we use the symbol L for inductance. L total equals L1 plus L2 plus L3, etc. So resistors and inductors are pretty much the same in the structure of the formula used to evaluate the equivalent. Of course, it's ohms for resistance and henries for inductance. And in parallel, the situation continues. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. And for inductors, 1 over LT equals 1 over L1 plus 1 over L2 plus 1 over L3, etc. So the odd one out then is capacitance. So CT for series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And for parallel capacitors, CT is equal to C1 plus C2 plus C3. So here we're looking at ohms, here we're looking at henries, and here we're looking at farads. So you can see there that the formula for capacitors is the other way round, if you like, from the formula for inductors and resistors. So that's something to bear in mind. So then the formula that you see there at the bottom of the screen, that one there, 1 over CT equals 1 over C1 plus 1 over C2 plus 1 over C3, that relates to capacitors in series. And this is a cause of a lot of mistakes. People get these formulae muddled up. I think if you remember the first two and just remember that capacitors are the other way around, then that should serve you well. Okay, again, don't worry if you haven't covered that yet and you find it a bit confusing. We're really just looking at in this demonstration at how we did on the calculator. So, clear that away, and we'll have a look at this formula then. Now, capacitors you'll tend to find not in farads, but in microfarads or nanofarads or picofarads. So let's take some values here of some capacitors in series. If we had, for example, C1, C2, and C3 in series, C1, C2, C3, and we put some values on here. Let's say this one was 0.1 microfarad. The C2 was 1000 nanofarads, and C3, I'll write the value up here, was, let's say, 0.09 microfarads. Now, if we were going to add those up, we could change them into farads in order to add them up. First of all, by putting noughts in the front and doing the decimal point hopping that we can do, or we can simply use a calculator to take the strain. So first of all, switch on the calculator, press the button again to clear the last value. Second function and engineering will make life a lot easier to start with. So the formula we're going to use is 1 over C1 plus 1 over C2 plus 1 over C3. Let's do C1 first. So C1 we can say is 0.1 EE 6 change sign. And you can see I've got 0.1 times 10 to the minus 6 microfarads. And I want to turn that upside down because at the moment I've put in 0.1 microfarads, but I want 1 over 0.1 microfarad because the formula, remember, is the formula you see below. 1 over Ct is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So I put C1 in and I want to get it the reciprocal of that, I want 1 over C1. So now I press the reciprocal button and I've got 10 times 10 to the 6th in the display. And now I want to do C2. So I say plus, and I put in 1000 EE 9 for nano, or 9 minus, change sign, for nano. So now you can see on the display I've got 1000 nanofarads in. Okay, and you can see that I want the reciprocal of that. And then I say plus 0.09 microfarads. Okay, so 0.09 EE 6 minus, and I want the reciprocal of that. And I press equals. So now I've got these three terms added together in the display. And it's 22.1 times 10 to the 6th or something like that. 22.1 recurring, and I've got a 0.6 up in the top corner. But of course, remember that is 1 over Ct equals that. So I need to flip what I've got in the display, in the X register, to get Ct. So I press 1 over X, and I get 45 0.2 times 10 to the minus 9, or to put it another way, 45 minus 9 is nanofarads. And I'm going to do a sanity check on that now to make sure I haven't had fat fingers during the use of the calculator. 0.1 microfarad, C1. Well, first of all, let's say we've got 3 capacitors in series. And because we're using the reciprocal formula, the answer has to be less than the smallest value that I've got there. So 1 microfarad would be 1000 nanofarads. And I've got 0.1 microfarad in C1, which is the same as 100 nanofarads. So that's an interesting figure. that this one here is equivalent to 100 nanofarads. This one is obviously 1000 nanofarads, and this one here is 90 nanofarads. 0.09 microfarad is 90 nanofarads. So I've got three values using the reciprocal formula, and it's got to be less than any one of them. Well, I can see here that I've got 100 and a 90 in the reciprocal formula. If those were the only two that I had, then I would get a value of half of the lowest, and that's about 45 nanofarad. And because this value is so much greater than the others, it isn't really affecting the calculation. So again, don't worry about that too much, but that is, if you like, a way of getting a sanity check to make absolutely sure that you're right and we don't just blindly rely on the calculator. It's a way of estimating what the result is likely to be. Okay, so that's looked at capacitors in series. 1 over Ct equals 1 over C1 plus 1 over C2 plus 1 over C3, etc. Alright, so let's have a look now at the next formula. Well, this is the one for capacitors in parallel. We've just said, I think, that the odd one out, if you like, from resistors, inductors, and capacitors is that capacitors in parallel, you add them up. Let's just look at a picture of that. So, or schematic diagram. We could draw three capacitors in parallel like this. And this wouldn't be too far, although this is schematic, this wouldn't be too far from what it might actually physically look like. So we know from our intermediate course that the capacitance of a capacitor depends on the area of the plates, the distance between them, the plates, and finally the dielectric in use. So here we have three in parallel. We made a little electrical connection between each one. You can see we've got a single capacitor with a much greater area. So that may be a good way of trying to remember that the CT, the total or equivalent capacitance of capacitors in parallel, you add them up, you add the capacitances together. And remember that in series we use the reciprocal formula. So I don't think we need to do that. This is a bit like resistors in series. We can just put the values in and add them up. And by now we should be getting fairly used to using the engineering notation, and you may well have to do that, the engineering button on the calculator, if you get values of nanofarads and picofarads, etc., etc., and that'll take the strain. Well, it's quite useful that we were just talking about the capacitors and what determines capacitance. If we actually wanted to find out what the value of a capacitor was, we could use this formula if we knew some things about the physical makeup of the capacitor. So here we have the formula for the capacitance, and if you look at the videos that I've produced on capacitance, you'll see some examples of being able to work through those formulae, and I think you by now should be able to manage that with the calculator. Okay, let's have a little look at the next row. Next row then, 1 over LT equals 1 over L1 plus 1 over L2, and it continues on 1 over L3. This is inductors in parallel. Inductance is in henries. You're probably going to find millihenries or microhenries, or maybe nano and picohenries perhaps in your calculations. You may find henries because in some large transformers would have an inductance of perhaps several henries. But there's no difference between, from the calculation point of view, between doing this type of calculation and doing the calculation for resistors in parallel. So this is inductors in parallel, and it shouldn't pose too much of a problem. Here they've put LT equals 1 over L1 plus 1 over L2. I don't know why they didn't say 1 over L3 in this example. It just continues on plus 1 over L4, etc. in the same way as the reciprocal formulas do for the other quantities that we need. So let's have a look over to the right. And here we have inductive reactance, XL equals 2 pi FL. Well, we'll go through this calculation because it gives us the opportunity to test out the pi key. So XL equals 2 pi FL. So here we have an inductor, not very well drawn, in a circuit, and we'd have some AC here, and the AC will have a frequency. And current will flow around the circuit. I'm going to call this IL, and the inductor will have a certain value in henries, L. Now remember that with an inductor, the higher the frequency, the greater the opposition to current flow, the greater the inductive reactance will be. And you may recall, we don't need this for the calculation per se, but you may recall there's a graph with frequency and XL, and basically at DC, when frequency is 0, the inductive reactance is 0 because there's no changing magnetic field, so there's no back EMF, so there's no opposition to current flow. And as the frequency increases, the inductive reactance increases. So let's say that the inductor L is equal to 0.5 henries, and let's say the frequency is equal to let's say 50 Hertz mains frequency. And the formula then for the inductive reactance XL equals 2 pi FL. So let's go to our calculator, switch it on, switch it off, switch it on, make sure everything's nice and clear. And it started off in float mode, and that's quite fine. That's not a problem. So we can say 0.5. Okay, oh, sorry, I'll start again then, so off, on. So we'll say 2 times, and I can just use the pi button now, pi times f, which is 50, times 0.5, because it's already in fundamental units, is equal to 157 ohms, because inductive reactance is in ohms. So that's 157 ohms. So that was simply a matter. If we go through the keystrokes, the keystrokes were on clear, 2 times the pi key, that was a little key, 2 times pi times 50 times 0.5, and then equals. So that's inductive reactance covered. This formula here, I don't know which row we're on, but working our way down the street. You may recall from the intermediate course that the abbreviation for impedance is Z. So that is impedance in ohms. Okay. We also talked on the intermediate course about scalar and vector quantities. We said that if there were I think I forget the analogy we used, but a tug-of-war team, and they were exactly in opposite directions, or they're pulling in the same direction, then we could talk about those as scalar quantities, and we can simply add them up. But where we've got some sort of direction involved, perhaps the teams are not pulling exactly at right angle, in line. Perhaps it's one of those traction tug-of-wars where you've got, the steam traction, and you've got a team of, my drawing's not going to be very good here, but you've got a team of people here exerting a force of, I don't know, let's say 100 newtons, not very much, but 100 newtons in that direction, and this is the tractor. Tractor's going in that direction, and you've got another couple of guys going this way. You've got 100 newtons there. You can't just add 100 and 100, because the resultant force is not 100 plus 100. You have to take into account the vector, in other words, the direction. And so you have to use some trigonometry, some Pythagoras, to figure out what the resultant force is going to be. Now we'll be covering that in lectures and in videos later on, so I won't dwell on that. We'll just look at the formula here. Let's say that we had a capacitor and an inductor and a resistor. Now the capacitor will have XC in one direction, and the inductor will have XL in another direction. Don't worry too much about that at the moment. We'll just say that the combination of these is some sort of reactance X after we've netted those off. And the resistor, because it is not a vector quantity, has a value R. So let's say we've got 10 ohms for the resistor and 15 ohms for the reactance there. Now we can't simply add the 10 and the 15 in the same way as we couldn't add the two tug-of-war teams directly together. We have to use a bit of Pythagoras to come up with the equivalent impedance the vector sum of the resistance and the reactance. So here we want to work out Z, so we say Z is equal to 10 squared plus 15 squared. Square root of the sum of those two. Z equals square root of 10 squared plus 15 squared. So let's do the stuff inside here first of all. And by the way, I should say at this point, there's no single way of doing these. I mean, you could use brackets to clump those together, or you could use memories to store intermediate results and things like that, but it's largely unnecessary. As long as we start sort of in the center of the equation and work our way out, we don't need to bother about those too much, and it's a lot more efficient. So clear the calculator, and we'll say 10 x squared plus 15 x squared equals. So this here is evaluated that is evaluated on the calculator to 325. So now I'm left with this, aren't I? Z equals the square root of 325. I simply press now the square root button here, and I've got 18. So 18 ohms is the impedance of that 10 ohm resistor and that 15 ohm reactance, which has come from XC and XL. Now XC and XL, because we assume that they are pure reactances, pure, work absolutely in opposition to each other. So sometimes you see this formula written like this. But in the notes that they've given you on the formula sheet, they've brought this down to a single value, indicating they're not going to make the calculation too complicated. They're going to give you the resultant impedance, if you like, or reactance of XC and XL before, during the questions. They won't ask you to work it out, but just in case you do encounter it. This one here is looking at voltages across resistors and capacitors, or resistors and inductors. So this one here refers to this sort of a circuit. Let's use VC first. Let me start again and get it in the same order as the formula. It'll keep it simpler. A resistor, and a capacitor, now going aside a minute, if that had been a resistor and a resistor, and if I'd had 2 volts across that resistor and 3 volts across this resistor, then Mr. Kirchhoff Kirchhoff, I'm going to spell this, Kirchhoff tells me that the voltage here was simply the 2 plus the 3. In other words, because they're resistors, I can add them in a scalar way, so it would be 5 volts. However, if I have 2 volts across here, and if I have 3 volts across here, I can't add them up to be 5 volts. I have to say that Vt here, Vt, is equal to the square root of Vr squared, voltage on the resistor squared, plus the voltage on the capacitor squared, and that should go right across the top. Now I won't do it again because in the formula sheet it says they're all VL squared, so I could equally well replace that with an inductor, and the story is the same. So let's work it out then. So here I go to the calculator on clear. Let's work out VR squared first. That would be 2x squared, and VC squared, so I'll add VC, plus 3x squared equals, that's 13. So this slot here evaluates to 13. So now Vt is equal to, equals down there, square root of 13. I've got 13 in my display already. I simply have to press the root key, and voila, the square root of 13, it turns out, is 3.6. And it's interesting to compare the fact that if it had been 2 resistors, it would have been 5 volts. But because we had a capacitive or inductive element in our circuit, we've got 3.6 volts instead. Now, a while ago we worked out the, I think it was one before last, we worked out the inductive reactance. Here we're going to work out the capacitive reactance. So Xc, capacitive reactance, equals 1 over 2 pi Fc. So we'll make this one the last one for this video, because otherwise the video will be excessively long, and I will pick up after this one with the remainder of the formulae. So, if you recall then, that if we have a circuit with an AC generator and we have a capacitor in it, at DC there's a break in the circuit, and so we drew a graph. If this is variable with frequency, if we start off at DC, then somewhere up here, close to the axis, but whatever, we would find the XC, we'll label the axis an F, a very high capacitive reactance. In fact, at DC it would be infinity if it was a perfect and pure capacitor. So we can't draw it joining the axis, we will join it, show it being asymptotal to the axis. That means very close, but never actually sort of touching it. And as we increase the frequency, the capacitive reactance comes down like that. If that was an inductor, we would have seen the opposite. I'm just going to draw it as a dotted line because it's not an inductor, so that's just to remind ourselves what it might be. So, to work out the capacitive reactance at a frequency along this scale here, okay, we use the formula Xc equals 1 over 2 pi root Fc, which is on your formula sheet, and that's what it refers to. Let's take, let's say, 1 microfarad, a fairly beefy capacitor, at 50 Hertz, and then Xc will equal to 1 over 2 pi times 50 times 1 times 10 to the minus 6. I should extend that because it's over the lot of them there, like that. Now, by now you should be looking at this thinking, well, I won't start with the 1, I'll start with the complicated bit at the bottom of the fraction there, and then flip it at the end. So let's work that out first of all. We've got, and we've also got some engineering notation, so I'm going to put it into engineering notation now. It doesn't matter if I forget, I can do it later on, but it keeps life easy. So I say 2 times pi times 50 times 1 EE 6 change sign, so EE minus, and evaluate that. So I've now evaluated the bottom of the fraction, and it's on the display of my calculator. I need to get 1 over that to get Xc, so I now press the 1 over X button, and the answer is 3.18 times 10 to the 3, and Xc is in ohms, so 3.18 times 10 to the 3 ohms. Or we could just make it, to be honest, we could just say 3, but I'm going to say 3.2 kilo ohms. So what we're saying is a 1 microfarad capacitor with 50 Hertz will provide an opposition to current flow of 3.2 kilo ohms. Or another way of putting that is that a 1 microfarad capacitor has a capacitive reactance of 3.2 kilo ohms at 50 Hertz. Of course, if it were at 100 Hertz, it would be different. You can see there that if I change this, made it 100, I would be halving that 3.2. It would be something like 1.6. And that's in line with the fact that as frequency goes up, capacitive reactance goes down. Okay, I think this is a good point to rule off so that this slide video doesn't get excessively long. Thank you very much, and we'll come back and do some more calculations from the formula sheet and using the Texas Instruments TI-30Xa a bit later on. Thanks very much indeed.